So we are playing with weaning ourselves off of the definition of the derivative. What's the definition of the derivative? So a derivative is a rate of change or slope function. So we take the derivative with respect to x of some function f of x, right? And what we're finding here is a rate of change function. Rate of change function. And we often call that function f prime of x. That's the rate of change function. How do we find such a function? We have to take the limit as h goes to 0 of the difference quotient, f of x plus h minus the original f of x, all divided by h. And we all know that is a burdensome, challenging process. Sometimes it is very, very difficult to do that. And what we're going to do today is we're going to wean ourselves off of this formula by observing some patterns, so we don't have to do this every time. We can say, hey, I know a pattern for this kind of problem. And we just have these shortcut rules. So again, we're going to wean ourselves off of this, wean off with some observations. These observations are going to lead us to shortcut rules. So we don't have to do that limit of the difference quotient every time we want to take a derivative, right? So super simple observation I'm going to make right now is suppose f of x was constant. So f of x is equal to some constant like 2. It's always equal to 2. Graph that. Here's y equals 1. There's y equals 2. Here's x equals 1. Here's x equals 2. Here's x equals -1. And y is trapped at being 2. Y is always 2. It's flat. What's the slope of a line like this? The slope of a line like this is always 0. So I expect the slope function to be 0. And if we take the limit of the difference quotient as h goes to 0 of f of x plus h, well, there is no x here. So regardless of what x is, f is always 2. Same thing here, 2 over h. So what's the limit as h goes to 0 of 0 over h? Well, 0 over h, now remember, limit means approach, but don't touch. So I'm not done here. As long as h is not 0, this right here is 0. And since there's no more h there, 0 is 0, done. That's the answer. And nothing special about 2. This could have been 17 pi. Then there would have been a 17 pi here and a 17 pi there, and there'd still be a 0 here and a 0 here and a 0 here. So we now have a new observation. Anytime we take the derivative with respect to x of a constant, like 2 or pi, the derivative is 0. What does this mean? We have a new shortcut rule we can just use and not have to do that anymore. Cool. So I'm just going to list a bunch of rules. I'm going to prove a couple of them, but I'm not going to prove all of them. Some of the proofs are in the book also. We're just going to go with the flow and start memorizing shortcuts so we can bypass this tedious process. Now, this is still important. This is the definition. Somebody says, what is a derivative? That is a derivative right there, right? But we're developing shortcut rules. All right, so collection of shortcut rules, and then I'm going to prove a couple of them. Shortcut rules for derivatives. And we'll do half of them today, and we'll do the other half tomorrow. So we're just going to practice the easy ones first. So I just mentioned one. Derivative with respect to x of a constant c is 0. Next, derivative with respect to x of x is 1. Right? Think about it. Y equals x, slope is 1. Sure, I buy that. The derivative with respect to x, oops, that's in the wrong spot there. The derivative with respect to x of a constant times a function. Because of the way limits behave, we can pop that constant out. We had a limit rule about that, and the derivative is a limit. is the constant times the derivative of the function. Which I can also write as c times f prime of x. So if there's a constant, we can pull that constant out, take the derivative, put it back together. The derivative with respect to x of the sum or difference of two functions, because limits of sum or differences behave nice if they exist, is you can just separate those and do them differently. So you can say, hey, what's the derivative of f of x? Find that. And then if you were adding, add it. If you were subtracting, subtract the derivative of g of x. We can separate them. This is true for sums and differences. It is not true for products nor quotients. We'll deal with those later. Those are much harder, much harder. And I think the biggest, most powerful one is what's called the power rule, that if you have the derivative with respect to x of x to the power n, and here for now, I'm going to restrict n to be a whole number. And you'll see why in a minute. So n in this case could be 0 or 1 or 2 or 3 and so on, but it couldn't be a fraction or a negative number yet. Later, we'll deal with that. Then that derivative is going to be n times x to the power n minus 1. And I'm going to go over why this is true next. So this is our first run at shortcut rules. And these rules combined means derivatives of polynomials are easy. So these rules here, this particular set, make derivatives of polynomials easy. Oops, new meals. Because a polynomial is just a sum of powers of x with a few multiples thrown in there, or maybe possibly a difference. And this basically describes how to take the derivative of a polynomial. So for example, let's do one right here and right now. If we wanted to take the derivative with respect to x of the function 2x to the third power minus 7x plus 256, we have a rule right here that says if you take the derivative of sum or a difference, you can just break it up to their individual derivatives. So cool. So this becomes the derivative of 2x to the third minus the derivative of 7x plus the derivative of 256. And then we have another rule that says if there's a multiple, we can just pop that multiple out. So I can pull that 2 out and then just take the derivative with respect to x of x cubed. And my rule here says pull the power down, then reduce the power. So that would be then multiplied by 3x squared. Ooh, excuse me. Minus, we can pop that 7 out. And then the derivative of x is 1 by my rule up there, the times. And then this is a constant right there. Derivative of a constant is 0. Cleaning this up, 2 times 3 is 6. X squared minus 7. That is f prime of x. If f of x was equal to 2x cubed minus 7x plus 56, or 256, excuse me. All right, so that's way easier than the difference quotient based on those rules there. In a moment, I'm going to justify the power rule, which is this sucker over here.